Welcome everyone. Today's topic is on Laplace transforms. First, let's go through an introduction. Some of this material will become clear when we do examples and theory. Using the Fourier transform, we already represented a signal as a linear combination of basic signals using the Eigen functions e to the power of j omega t. Then we could represent a given LTI system as a spectrum of eigenvalues as a function of omega, which is the change in amplitude that the system applies to each of the basic inputs e to the power of j omega t. Now we study a generalization of the Fourier transform referred to as a Laplace transform. The Laplace transform converges for a broader class of signals than does the Fourier transform. So particularly we will look at this point later on. The general class of eigenfunctions for LTI systems consists of complex exponential e to the power of st. So we have been considering e to the power of j omega t when we studied the Fourier transform, and now we will study this more generalized form where s is equal to sigma plus j omega. So it is a complex number expressed in a Cartesian form. So when we set sigma equal to 0, when s is purely imaginary, that means s is equal to j omega, the Laplace transform reduces to the Fourier transform. The Laplace transform is a Fourier transform of an exponentially weighted signal. Therefore, the Laplace transform can converge for signals for which the Fourier transform does not converge. So you can think about the Laplace transform as the Fourier transform of a signal that is weighted by an e to the power of minus sigma t. So where sigma causes the signal to attenuate at certain ranges of time so that we are able to integrate that. The ranges of values for s of h s for which the Laplace transform converges is called the region of convergence. For some values, this is integrable. For some values, it is not. So those values of h for which this is integrable is called the region of convergence. So therefore, it is very important to express the region of convergence also when you express the algebraic expression of the Laplace transform. So when you say Laplace transform, it is the algebraic expression and the region of convergence expressed together. So in other words, you can have the same identical algebraic expression and two regions of convergence representing two entirely different signals. So two different signals can have the Laplace transform with identical algebraic signals, expressions, and differing only in the region of convergence. Okay, let's recall the continuous time Fourier transform. So for some purpose, I am avoiding writing j omega, but writing omega to make a point. So xt 1 over 2 pi integral from minus infinity to infinity x omega e to the power of j omega t d omega. This is the synthesis equation, and we have the analysis equation x omega is equal to integral from infinity to infinity xt to the power of minus j omega t dt. So when we consider an LTI system, and if the impulse response is ht, and if you send a signal like j omega t, so the output will also look like e to the power of j omega t, just multiplied by this sort of constant, that means independent of time, which we call the eigenvalue. So that is actually the Fourier transform of this system's impulse response. So this is the point that we mentioned over here. We could represent a given LTI system as a spectrum of eigenvalues as a function of omega, which is the change in amplitude that system applies to each of the basic inputs e to the power of j omega t. So that means h omega applies that amplitude change to this particular exponential signal. So this same phenomena is there for the Laplace transform also. So let's consider this eigenfunction property of the Laplace transform. So what we consider is, we consider an LTI system with ht impulse response and apply to that this signal e to the power of st. E to the power of st and see what we would get out of that. So to see what we would get out of that, we have to carry out the convolution integral. So you can see it is h tau e to the power of st minus tau d tau. So in this expression, the integral is on tau. So therefore, the e to the power of st, which is independent of tau, can be taken out. So you can see the signal est gave rise to the same signal est multiplied by some constant hs, which is independent of time. So this, as you remember, we call it the eigenvalue, and this is an eigenfunction. So hs in this case is integral from minus infinity to infinity h tau e to the power of minus s tau d tau, very similar to the Fourier transform analysis expression that we had. Okay, so therefore the Laplace transform of a signal xt, which is xs, is equal to integral from minus infinity to infinity xt to the power of minus st dt. So we symbolize that using this. Xt has the Laplace transform xs, and we must remember that s is equal to sigma plus j omega. So if we take the Laplace transform xs and we set s equals j omega, that means set sigma equals to 0, then you will get the Fourier transform of that signal. So if you think about the convergence of the Laplace transform, so we know that when we take the Laplace transform and we set s equals j omega, we are going to get the Fourier transform. Xs, to remind, is infinity to infinity xt to the power of minus st dt. So we explicitly write s equals sigma plus j omega. So we have to write sigma plus j omega over there. So what this means is xt multiplied by e to the power of minus sigma t times e to the power of minus j omega t dt. So now we remember the expression for the Fourier transform of a signal, let's say at. So a j omega is equal to minus infinity to infinity at e to the power of minus j omega t dt. So therefore we realize that if we think that this is the signal, xt to the power of sigma t is the signal, then actually this is a Fourier transform of that. So you can see xt has been exponentially weighted. So therefore, although xt cannot be integrated in this fashion, maybe this quantity can be integrated for some ranges of sigma. So this is why we say that Laplace transform may converge for signals that the Fourier transform does not converge. So Laplace transform may converge when Fourier transform does not. Okay, now we can take an example. Xt is equal to e to the power of minus 80 ut. So therefore, you can see this ut is like this. So this is t, cannot grow t for some reason. So this is 1. So therefore, what is e to the power of minus 80 when t is equal to 0? It's like this, and if a is positive, so it goes like that. So this region is cut off. Okay, xs is equal to minus infinity to infinity xt e to the power of minus st dt. So since we are using this signal, we can write it as 0 to infinity e to the power of minus 80 e to the power of minus st dt. Because of ut, we decided to integrate from 0 to infinity. So when we try to integrate this, let's see, we have e to the power of minus a plus s t that has to be integrated from 0 to infinity. So we want to write this as 1 over minus a plus s and e to the power of minus a plus s t 0 to infinity, and we want to apply the limits. When we want to apply the limits, when we are setting t equals infinity, we want to write that as 0. To write that as 0, we have to consider this e to the power of minus at times e to the power of minus st is there. So we have to gather the real parts, e to the power of minus a plus sigma t e to the power minus j omega t. So therefore you can see this one has the magnitude 1, and this is the one that contributes to magnitudes other than unity. So therefore we have to see for this to be written as 0 minus a plus sigma must be greater than 0. So actually this one is the real part of S, right? Sigma is the real part of S because S is equal to sigma plus j omega. So this is why we have to write, when we write 1 over a plus S 0, we have to at once write sigma is greater than minus a. In other words, the real part of S is greater than minus a. And of course, when we put t equals 0, you will get 1 here. So it is 1 over a plus S. Real part of S is greater than minus a. Like this. So therefore, you see, it is very important for us to write the region of convergence. If the region of convergence is not written, the expression cannot be written in this fashion. Okay, now let's consider this signal e to the power of minus e. So xt is equal to minus e to the power minus at u minus t. So u minus t is this kind of a signal. So now let's see how we can do this. So xs is equal to minus infinity to infinity xt e to the power of minus st dt. What this means is we are integrating from minus infinity to 0, because here u minus t minus e to the power minus at e to the power minus st dt. So therefore minus infinity to 0, we can now write the answer to the integral. So minus 1 over minus a plus s e to the power minus a plus st minus infinity and 0. So therefore it's 1 over a plus s. We have to put 0 first, and that is 1, and then we want to write 0 here. So when we write 0 here, what we are saying is e to the power of minus a plus sigma t e to the power minus j omega t is this quantity. And then if you want to substitute minus infinity here, what we are saying is a plus sigma must be less than 0. This is actually real part of S. So real part of S is less than minus a. So that's why we have to write it at once. So equals 1 over a plus s. Real part of S is less than minus a. So you can see both these signals xt equals e to the power of minus at ut, which we considered in the previous slide, and this one. Both these have the same algebraic expression as the Laplace transform, differing in the region of convergence. So for the previous signal, we had xs equals 1 over a plus s, and real part of s is greater than minus a. Okay, so that's why it's very important to write the region of convergence. So let's take one more example. Find the Laplace transform of e to the power of minus t ut, e to the power of minus 2t ut. So we know the Laplace transform of e to the power of minus at ut has the Laplace transform 1 over s plus a. The real part of s is greater than minus a. So therefore we can write the Laplace transform of e to the power minus t ut as 1 over s plus 1. Real part of s is greater than minus 1. So here you can see a is equal to 1, and here a is equal to 2. So therefore 1 over s plus 2. So therefore if you sum them, you have the Laplace transform as this when you add these two terms. So when you investigate this polynomial rational, this has a numerator and a denominator. Numerator is equal to 2s plus 3. Denominator is s plus 1, s plus 2. So when the numerator is equal to 0, we have the so-called zeros. Values of h for which the numerator is 0 are called zeros. Values of h for which the denominator is 0 are called poles. So what is the value of s for which the numerator is 0? So s is equal to minus 3 over 2. So that's a 0. We show that using a circle. Zeros are shown using circles, empty circles. So what are the two zeros? So when the denominator is 0, that means s plus 1, s plus 2 is 0. What that means is s equals plus s equals minus 1 or s equals minus 2. These are the zeros which we represent using crosses. Also we notice that these are the two regions of convergence for the two expressions. We have to find the common region. A common region is real part of s is greater than minus 1, which we have highlighted here, shaded here. Okay. Alright, now the properties of the region of convergence. Region of convergence contains no poles. If there is a pole, the Laplace transform goes to infinity. So therefore you can see region of convergence cannot contain poles. The region of convergence of x's, a small s, consists of strips, not strips parallel to the j omega axis in the s plane. So you see regions of convergence sometimes are like this, sometimes regions of convergence are like this, sometimes they are like this. Anyways, they are strips. So these lines are parallel to the j omega axis. Fourier transform of xt converges. If it converges, what that means is implies and is implied by the ROC includes the j omega axis in the s plane. So we know that the Laplace transform reduces to the Fourier transform on the j omega axis. So s is equal to sigma plus j omega. So when sigma is equal to 0, we get s equals j omega. That means Fourier transform. So sigma is 0 on the j omega axis. This is our j omega axis, right? This is sigma. Okay. So let's take one more example. Sketch the choices of the ROC associated with x is equals 1 over s plus 1, s plus 2. So the two poles are minus 1 and minus 2, which I have plotted. So one region of convergence is this, greater than minus 1, and this one. Another region of convergence is between that strip. Another region of convergence is less than minus 2. This is another strip. So we had to know about the time domain signal to know which one is the actual region of convergence. So now let's think about finite duration signal from t1 to t2. So it's finite, here it's 0 and here it's 0. If xt is a finite duration signal, then the ROC is the entire plane. That means when you multiply this with e to the power of minus sigma t, you can integrate this because this one itself can be integrated. So we multiply it with the decaying exponential, for example, or an increasing exponential, for example, it can be integrated. So now let's consider this case. So this is a right-sided signal. So from t1 to minus infinity is 0, but it continues toward plus infinity. If xt is a right-sided signal and real part of s equals sigma naught is in ROC. What this means is, if you multiply that with e to the power minus sigma naught t, we can integrate. We know that. That's why we say it is in the region of convergence. Then think about another sigma value which is actually higher than sigma naught, like the orange one. So if we multiply with this red curve, if we can integrate, if we multiply with the fast decaying signal, it should be integrable. So therefore, for any region, real part of S, that means actually sigma 1, you can think sigma is greater than sigma naught are in the ROC. So we have to remember this. If X3 is right-sided and real part of S equals sigma naught is in the ROC, then all values for which real part of S is greater than sigma naught are in the ROC. If X3 is right-sided and X3 is rational, then ROC is the right of the rightmost pole. And we also know that the ROC cannot contain poles, and here we say it's greater than sigma naught. So therefore, when we combine these arguments, we know that the region of convergence must be to the right of the rightmost pole. If X3 is left-sided and real part of S equals sigma naught is in the ROC, then all values for which real part of S is less than sigma naught are in the ROC. So you can argue it out and see. I will not show that using a diagram. If X is left-sided and XS is rational, then ROC is the left of the leftmost pole. Left of the leftmost pole. So we are considering about something like this. Two poles, let's consider. So the ROC is like this. So don't think that poles are always on the real this axis, but they can come in conjugate pairs also. So we will see this later. So like this, these kind of situations can happen. So if we consider two-sided signal, if the ROC of a two-sided signal, if Xt is two-sided and real part of S is equals sigma naught z is in the ROC, then ROC is a strip in the S plane. If the Laplace transform xs of xt is rational, then if xt is right-sided, the ROC is the region in the S-plane region in the S-plane to the right of the rightmost pole. If xt is left-sided, the ROC is in the region in the S-plane to the left of the leftmost pole. So as a summary, memorize that. So we can take an example. The Laplace transform is specified by xs equals 1 over s plus 1 s plus 2, and we are given that real part of s is greater than minus 1. So therefore, when we drew the pole zero plots, so here s equals minus 1 and s equals minus 2 are the poles, and we notice that it is the region of convergence is to the right of the rightmost pole. So this is the rightmost pole. Rightmost pole, and ROC is to the right of the rightmost pole. So therefore, this must be a right-sided signal. So then the choices are in this case e to the power of minus at ut signal or minus e to the power of minus at u minus t signal. So between these we have to make a choice, and we make that choice based on the region of convergence. So you see, so we have obtained the partial fractions of this, and we know that the real part of s is greater than minus 1. It's given in the sum. So consider x1 is 1 over s plus 1. So let's consider this expression first. So x1t is e to the power of minus t ut because of this region of convergence. Otherwise, you have to use the other expression minus e to the power of minus t u minus t. And then let's consider x2t, the second term, that also is good because it is anyways real part of s is greater than minus 1. That means real part of x is greater than minus 2 anyways. So therefore x2t also turns out to be minus e to the power of minus 2t ut, and when we combine we get this expression. So you can see it's a right-sided signal because we have ut. Okay. One more example. Find the inverse Laplace transform of xs equals 2s plus 4 divided by x squared plus 4s plus 3. Real part of s is greater than minus 1 and another less than minus 3, and between this. So these three conditions. So you obtain the partial fractions 1 over s plus 1, 1 over s plus 3. The ROC of xs is if the ROC of xs is real part of s is greater than minus 1, thus xt is a right-sided signal. So we can quickly draw the pole zero diagram, and we realize that the poles are -1 and -3, and we have been given a real part of s is greater than -1. So for both these expressions we write right-sided signals, therefore this one. And in the second case, the ROC of xs is real part of s less than -3, so therefore xt is a left-sided signal, so therefore we have to write -e to the power minus t u minus t signals. See, based on the region of convergence, we have to write e to the power minus at ut signal, or minus e to the power minus at u minus t signal. Okay. Then the third case, the ROC of xs is between -3 and -1. Thus, xt is a double-sided signal. So you can think about it. So it's greater than real part of s is greater than -3. Therefore, for that one, it's a right-sided signal, but it's less than -1. So for this one, it's a left-sided signal. Okay, then we remember these Laplace transform pairs. So for delta t, the Laplace transform is 1 or less. For ut, it's 1 over s. So you can quickly see, because we know e to the power of minus at ut's Laplace transform is 1 over s plus a. So when a is equal to 0, you can see, you can get 1 over s from there for ut. Minus u minus t 1 over s once again. So see the region of convergence. Tut 1 over s squared, tn minus 1 divided by factorial of n minus 1 ut 1 over s n, and so on. So e to the power minus at ut, we know that now, we are very familiar with that. Minus e to the power minus at u minus t. So in an exam situation, these will be given to you, but it's these and few of those. It's good to remember these things. Okay. Now let's look at the properties of Laplace transforms briefly. So first of all, the linearity property. If we have two signals x1t and x2t, and you multiply them by constants a and b, the corresponding Laplace transforms are multiplied by those same constants. If you differentiate a signal, its Laplace transform is the original Laplace transform multiplied by s. So we saw a similar relationship in regard to the Fourier transform also. By the way, I forgot to mention that since Laplace transform is xs, and s is equal to sigma plus j omega, and when we set xs s equals j omega and get the Fourier transform, we write for Fourier transform x j omega. I forgot to mention that. Okay, if we have system xt is the input, output is yt, and impulse response is ht, their Laplace transforms are xs, hs, and ys. Ys is xs times hs. This is the convolution property. So yt is ht convolved with xt, and if you get the corresponding Laplace transforms, you can see that ys becomes hs times x times xs. So you can see the convolution operator becomes multiplication in the Laplace domain, which is so in the Fourier transforms also. Also, if the system is stable and causal, all poles are in the left half of S-plane. We'll see that later also. So I have listed the properties of Laplace transform. So you can verify most of these things on your own. And then the initial and final value theorems. So the signal value at 0 plus just after 0 can be found by multiplying the Laplace transform with s and setting s to 0. And the final value theorem, when t goes to infinity, value of xt is s xs set x to 0. These are the properties of the Laplace transform. And the convolution is the multiplication. Derivative is x s times xs. It's very important to remember that. And when you have minus t xt, you have d by ds xs, and so on. So corresponding regions of convergence are also listed there. So we can verify the time shifting property. T minus t naught is equal to e to the power of minus s t naught xs. We saw a similar relationship in regard to other transforms. Xt minus t naught's Laplace transform we can write as xt minus t naught e to the minus power of minus st dt. And we do the variable substitution, tau equals t minus t naught, and we obtain this. So for t we put tau plus t naught, and then what is not related to dt we take out, and we realize that this is the Laplace transform with the same ROC as xs itself. Okay, from properties we can do this example. We will do a few of them. Use the various Laplace transform properties. Derive the Laplace transform of the following signals from the Laplace transform of ut. So for ut e to the power, for ut, Laplace transform ut e to the power of minus st dt, and we have 0 to infinity e to the power of minus st dt, 1 over s minus 1 over s e to the power of minus st, 0 to infinity. And if real part of s is greater than 0, then we can write it as 1 over s, similar to e to the power of minus at ut arguments that we made. So delta t is the derivative of dut by dt. So if you want to get the derivative of a signal, we have to multiply the Laplace transform by s. Laplace transform of a derivative of a signal. You can see you multiply the Laplace transform by s. So therefore the Laplace transform delta t, as we would expect, is 1. Then again, applying the differentiation property to all results above, we obtain Laplace of s prime t, delta prime t is s for all s. Using differentiation property in s, we can have tut's Laplace transform is minus d by ds 1 over s, that is 1 over s squared. So then using the shifting property in s domain property, we can have e to the power of minus at ut 1 over s plus a. That means we know the Laplace transform of ut, that's 1 over s. Now how do you obtain Laplace transform? When you multiply that with e to the power of minus at, then we can look at the property. So like this, e to the power of minus s naught t, e to the power of s naught t, if you multiply that, you will get s minus s naught. So we multiply that with e to the power of minus at, so therefore we have to have s plus a instead of x. So others you can do on your own. So next we'll do the analysis of LTI systems using the Laplace transform. Thank you.